So my name is Odd Andersen, and in this talk I will give a quick introduction to poroelasticity in MRST. There are many examples where we want to understand the mechanical behavior of the subsurface and how this is influenced by the flow of fluids. The underground can be thought of as a porous sponge where the mechanical behavior is impacted both by the properties of the solid sponge or rock matrix and the flow and pressure of the fluids it is filled with. And as long as the actual deformations are small compared to the extent of the domain under study, which is frequently the case, linear poroelasticity is a useful framework to model this behavior. It combines the equations for weakly compressible fluid flow with the mechanics equations of linear elasticity. The goal of this presentation is to provide a very brief overview of linear poroelastic theory and show how this can be modeled using the tools provided by the MATLAB Reservoir Simulation Toolbox, or MRST. The code for the examples shown here are also provided directly in the AED mechanics module, and they are discussed more in depth in the last chapter of our open access book. So first, a little bit about theory. So linear elasticity. We'll start with that. Linear elasticity is the study of stresses and strains in an elastic continuum under small reversible deformations. By infinitesimal deformations, we mean that the displacements are negligible compared to the size of the domain. When it comes to forces and deformations in a solid material, the concept of strains and stresses are central. I will try to give a very brief explanation. Strains refer to change in distance between points inside a solid in the deformed state as compared to the reference state. Strain is a unitless quantity as it refers to the change of distance per distance. You can call it a stretch of the material. We consider here infinitesimal strains, which also means that we do not have to operate with different coordinate systems between the original and the deformed state. Strains have orientations, and a 3x3 strain matrix captures the strain state in 3D space. This is a symmetric matrix that can be diagonalized to identify the three principal strain directions and magnitudes. Stresses, on the other hand, express internal forces per unit area, and they thus have the unit of pressure. The stress state at a point in a solid can be expressed as a 3x3 matrix. And in linear elasticity, stresses are related to strains through Hooke's law, which involves the rank 4 tensor C. For sufficiently simple materials, the C tensor can be defined in terms of 2 degrees of freedom, that is, 2 elastic constants. And these can be chosen in many equivalent ways. For instance, as we can see here, the Young's modulus and Poisson's ratio can be used to characterize the material. The force equilibrium equation represents the static version of Newton's second law, applied to each point of a continuous solid. At each point inside the solid, the divergence of the stress tensor equals the body force, which is typically gravity for geoscience applications. In addition, boundary conditions must be specified. These can be in the form of imposed stresses, like a Neumann boundary, or gamma sigma down here, or imposed strains, which is a Dirichlet boundary, or gamma u here. Note that the boundary conditions may be different for different spatial directions. For instance, a typical setup is shown on the right with roller boundary conditions applied on the lateral side of this geologic domain. Under these conditions, the lateral displacement is fixed, whereas the vertical displacement is free and subject to a typically zero force. Since stresses are linearly related to strains and strains to displacements, the force equilibrium equation can be written as an equation with displacements as the unknown. For instance, by representing the C tensor using Young's modulus and Poisson's ratio, the 3D equation for displacement reads like what you can see in the middle of this slide. So now we move to poroelasticity. In poroelasticity, the solid is considered porous, and its pore space is filled with a fluid with its own pressure field. The pressure impacts the stresses between the grains of the solid, and we get the concept of effective stress, which is a stress tensor with a pressure term added on. In addition, pressure is dictated by the fluid flow equation based on conservation of mass for the compressible fluid, coupled with Darcy's law that couples the flow of the fluid with the pressure. And put together, we can see that the mechanics and flow equations are coupled in two ways. First, the accumulation term of the flow equation contains a term that represents bulk volume change, which is directly related to the mechanical strain. Moreover, fluid pressure is present in both equations, since we are dealing with effective stress. For the linear elastic system, we needed two constants, but now with the poroelastic system, we need four. In addition to the two linear elastic constants, we here have the Biot-Willis parameter alpha, as well as the constrained specific storage coefficient S epsilon. And there are, of course, equivalent choices, but to define the system, 4 degrees of freedom needs to be specified. So I just mentioned that there are many possible choices for poroelastic constants in order to specify the system completely. Here on the right is a list of some that you may encounter in the wild. Their definitions are based on different physical assumptions and the nature of what they represent. However, since there are only 4 degrees of freedom to specify the basic poroelastic system, it is clear that these are all related. The theoretical relationships between each of them can, however, be quite complex and lead to annoying extra calculations to convert between them to get the ones that you are interested in. One example on the lower left side here, if we operate with an assumption of negligible lateral strain, we can get rid of the term in the fluid flow equation that depends on the mechanical strain. And we can therefore solve the fluid flow independently of the mechanics, so uncoupled. And this is typically what is done in practice in a traditional reservoir simulator that doesn't use mechanics, using a pore volume multiplier. However, for this to remain consistent with the mechanics equations, if we are working with a full system, the correct value for this multiplier must be chosen, and this involves knowledge of several poroelastic parameters, such as the Biot-Willis parameter alpha, the Gertzma parameter Cm, and the bulk modulus K. So in some cases, the mechanics and flow parts of the system are weakly coupled, and the mechanics can be computed in a post-processing step after having solved the flow problem separately. In other cases, the coupling is strong enough that the equations must be solved together. In that case, you can either choose to solve the equations together as a combined linear system, which is fully coupled, or to use a sequential splitting scheme where you alternate between solving the mechanics and the flow equations in a staggered or iterative manner. There are several ways to do this, and they are not all equally stable. The best approach that I am aware of is the fixed stress split method, where you first solve the fluid equation under the assumption of constant stress, and then the mechanics equation. So I will now talk about linear poroelasticity in MRST. MRST provides functionality for solving linear elasticity problems in the vemmech module with the VEM linelast function. This function uses a spatial discretization based on the virtual element formulation, which can be easier to work with than finite elements on complex grids, as is typically the case with industry standard reservoir simulation grids. The poroelastic module that combines mechanics and flow is called AD mechanics. And in addition, I would like to highlight a useful little tool provided with AD mechanics that allows you to convert instantly between different poroelastic parameters and moduli without having to do complex calculations. So the AD mechanics module provides both fully coupled and sequential splitting strategies. So the first 3 models here on top use a fully coupled formulation, and they are implemented separately for 1-phase, 2-phase, and 3-phase black void. The last model uses sequential coupling based on the fixed stress split scheme for any fluid system. AD Mechanics also contains several example scripts, including full versions of the examples that I will present you with shortly. So the aforementioned poroelastic tool is found in AD Mechanics. It allows you to compute all the poroelastic constants that can be deduced from the values that you already have, without having to wade through definitions and algebraic relationships. For instance, on the left here, on the left side, we call poroparams with three constants that we have available. In this case, K, the bulk modulus, and two other moduli, H and R. And it returns a structure where all constants that can be deduced from these have been calculated, and those that cannot are left as not a number. In this example, there are many not a number values because none of the constants that we provided in this call have any relation to shear. So if we do the same call, but now we include the shear modulus G, in the example to the right, the script is now able to compute all the poroelastic constants. I will now illustrate the use of poroelasticity simulation in MRST. The first example I will show is called Terzaghi's problem and concerns the compression of a cylinder consisting of a porous, fluid-filled medium. The problem can be directly related to the study of soil consolidation, where the ground is slowly sinking due to heavy infrastructure installed on the surface. The problem can here be posed as follows. We consider a cylinder of porous and fluid-filled medium. Its bottom is clamped and its lateral sides are free to move in the vertical direction only. The top surface is open to fluid flow, whereas the bottom and lateral sides are closed. At t equal t0, a load F is applied to the top surface, which causes an immediate downward displacement, followed by a slow, gradual creep downwards as water is gradually expelled from the top. And we measure the vertical displacement on the top surface and fluid pressure. The full code listing is provided in the AD Mechanics example and in the book, but I would like to show some highlights. On the upper left side, we see the specification of boundary conditions. We have already constructed the grid and identified the indices of the bottom nodes and the top faces. We create a struct called LBC, which contains two fields, one for displacement boundary conditions, which applies to individual nodes, and one for force boundary conditions, which apply to faces. Likewise, a body force is defined on the upper right. Gravity is set to 0 in this example, so the body force is effectively 0, but needs to be provided nevertheless. On the lower left, we construct the actual model after having prepared the rock and fluid objects as well as the mechanical problem. A note here on the middle in this second block that the pore volume multiplier is set to be consistent with the chosen poroelastic parameters, according to the formula we saw a few slides ago. The initial state sets 0 fluid pressure and 0 initial displacement. And we specify a schedule, which defines time steps, and then run the simulation on the lower right side with simulate schedule AD. And if you look at the results, on the left, we see the vertical displacement of the top surface and how it evolves over time. So we note that there is an immediate downward displacement of about 1.6 centimeters once the load is applied. And this displacement increases to around 2.8 centimeters when the characteristic time of the system has been reached. The evolution of the dimensionless fluid pressure is shown in the middle. The length of the cylinder is along the x-axis here. And we see how pressure rises to 1 when the load is initially applied, and then gradually dissipates towards 0 again throughout the column as water is expelled. Another fundamental poroelastic problem is Mandel's problem, which is interesting because it exhibits a unique poroelastic effect that is only manifest through the coupling of mechanics and flow. We start with a slab of poroelastic fluid-filled material interposed between two parallel rigid and impermeable plates. The problem here is considered in 2 dimensions. There are 0 stress conditions on the lateral sides and roller boundary conditions on the top and bottom. Initial fluid pressure is 0. At T equals T0, a force F is applied normally to the plates and held constant. This will cause the material to gradually compress. The induced pressure causes fluid to gradually evacuate from the sides. And the Mandel-Cryer effect is the fact that fluid pressure at the center line here initially increases before starting to decrease. This problem is also somewhat challenging to model since the top and boundary conditions are not trivial. Since the plates here are considered to be fully rigid, the vertical displacement has to be uniform, suggesting that we impose a displacement boundary condition. However, what we have gotten is the integrated force over the plate. That's what's given, but that is not going to be uniform along the length of the model. So MRST, we model this through using an inner loop at each time step, as I've shown the relevant listing on the right here. So this inner loop searches for the correct amount of plate displacement so that the integrated force has the correct value. And that means that we cannot use simulate schedule AD on the whole schedule at a time, but we need to run it separately for each time step. The details on this are given in the book chapter. So we here see the result of the simulation. The right side plots the fluid pressure profile from the center of the domain out to the right boundary for different points in time. We see that the pressure generally decreases over time, except for the very beginning at the center of the model, where we observe the Mandel-Cryer effect, circled here in red. So to round off, I think it's appropriate to at least briefly show some examples that honor the R in MRST, namely reservoir simulation. Here is another example that can be found in AD mechanics, where we model fluid injection into the known field and the impact it has on the surrounding rock. On the left, we see a plot of the fluid pressure at the end of our simulation, and on the right, the corresponding vertical displacement of the rock. We see here that the area above the injection has been displaced upwards, and the area immediately below it has been compressed downwards in this yellow color. Note that the virtual element model discretization comes in handy here, since the grid have some quite distorted cells. Here's another example from a couple of years back, and this is a static calibration problem where we try to deduce the stress field from measurements at the geological site in Michigan called Perch. This was a research project that we did in collaboration with the American Research Institute Battelle and financed by the US Department of Energy. So in this project, we have access to partial stress tensor measurements from several wells in the area and some seismic data. The geologists also constructed a static earth model of layer cake type, where each geological layer had its own mechanical properties. We then combined the use of MRST mechanics modeling with the adjoint-based optimization capabilities that Stein will talk about tomorrow, in order to determine the stress boundary conditions, that is the far-field stress magnitudes and orientation, as well as to tune or to adjust the material parameters of the rock, so that when we compute the stress field, we obtain a field that corresponds as closely as possible with the observed data. And by using this adjoint-based optimization framework, we can do this automatically, and we get the sort of optimal configuration of the parameters and stress. So by that, I will round off this presentation, and I thank you for your attention, and I'm ready to answer questions if you have them. Thank you.